Couple of days ago, a perceptive student asked some good questions about the Kelvin-Planck statement related to the second law, and that really got my wheels turning. And I wanted to go ahead then and provide a couple of more thoughts and remarks about the Kelvin-Planck statement. In other words, one of the three statements of the second law of thermodynamics. Great. Well, finally, we have the title slide up. And so remember that there are three statements of the second law of thermodynamics. And to try to summarize all of them, remember that all three of those statements involve talking about things that are possible in the real world or impossible to accomplish. And so the Kelvin-Planck statement is one of those. And here's the statement of the Kelvin-Planck, the Kelvin-Planck statement of the second law. And remember that in the introduction to the second law of thermodynamics, I have a video, and most instructors have a lecture going through all three statements of the second law. And so this is just a screenshot. This is a copy and paste slide from that presentation. And what does it say? It says that this schematic is impossible. In other words, it's impossible to operate in a cycle. Here's a black box operating in a cycle in which you take in heat from a high temperature reservoir and you convert all of that heat transfer into work. That is impossible. That's a statement of the second law. Impossible to operate in a cycle and transform heat directly into work. Well, here's what is possible. And I want to show this for comparison. Well, here's our system operating in a cycle. So a statement that is possible is that you've got heat transfer in from a high temperature reservoir. You can convert a good proportion of that heat into work. But the second law, Kelvin-Planck statement, says you must reject some heat, at least some heat must be rejected to a low temperature reservoir. And the student's perceptive question really got my wheels turning and thinking about my own experience as a student and how I was doing some thinking about this and thinking, wait a minute, we've had some homework problems in this class already in which we've been transforming heat into work. And gosh, that confuses me because we've had some problems that have been representative as possible. And I've got this situation. And this made me think about my undergraduate experience in which one of my thermo professors was the department head at the time, Dr. J.B. Jones. And I did not have the nerve to bring up that question, my confusion. I didn't have the nerve to bring this up to Dr. Jones in class because none of us in the class wanted Dr. Jones to be disappointed in us. And I was so afraid at bringing up this question because I was afraid that Dr. Jones would say, gosh, Jay, I'm disappointed that you don't fully understand the Kelvin-Planck statement. So I kept my mouth shut as an undergraduate. I decided to go to graduate school. And of course, we take more advanced thermodynamics classes in graduate school. And Dr. O'Brien, who ultimately became department head of the ME department, he was my professor. And I was able to gather up the nerve, the bravery to ask in class to Dr. O'Brien a question about, gosh, we've had some homework problems that are transforming heat into work. Why is that not a violation of the Kelvin-Planck statement? And to his credit, he very respectfully, got a smile on his face, and very respectfully answered my question. And so I'd like to take this video and maybe go through sort of like the question I asked to Dr. O'Brien and maybe try to fully more explain to you if you're struggling with statements of the second law of thermodynamics, Maybe this will help you better understand the Kelvin-Planck statement the way Dr. O'Brien's guidance did to me at the graduate level. And so as I was sort of asking my question in class, I couched it in terms of an example problem, and this is a representative of what I think I asked. And so here's an example problem. Let's work out together. It says it should be familiar, and it should be like child's play to you now. You should be really good at solving this problem. It says zero point 0.1 kilograms of argon is contained in a piston and cylinder. Okay. The initial pressure of the argon is 200 kPa, and the initial temperature is 280 degrees K. Heat is added to the argon in an isothermal process until its volume doubles. We're adding heat at constant temperature. And here's the 3 homework questions. What is the final pressure of the argon? How much work is done during this process? How much heat is added during this process? Let's solve this problem. And you kind of go along, think ahead before we go through the solution together. Let's start with a sketch and plan what we're going to do before we put pencil to paper. We've got a closed system. It's a piston and cylinder. The mass is fixed. M1 equals M2. It's an ideal gas. It's argon. It's a monatomic gas. We remember the ideal gas equation of state, PV equals MRT. That's going to help us, isn't it? Let's look at our sketch. Here's our piston and cylinder. Here we are at state 1. I'm showing heat added, work being done. The volume is doubling, which was given in the problem statement. I'm writing down that T2 equals T1. It's an isothermal process, and I'm depicting my new closed system. Went from state 1 to state 2. All right, we're going to solve this problem. We're going to answer the questions. Well, how will we attack it? Well, let's see. Let's solve for V1 first with the ideal gas equation of state. P1 V1 equals MRT1, and check off what we know from the given information. Okay, got it. We'll find V1. Given in the problem, it said the volume doubles, so V2 equals 2V1. That's pretty easy. And the question was, what's the final pressure? Well, final pressure. We'll use the ideal gas equation of state again. So P2V2 equals MRT2. And what's T2? T2 is exactly equal to T1. So we've got the pressure made. Next question was, what's the work done? We will draw a pressure volume diagram because we know the path. We know the process path. PV equals constant equals MRT. Isothermal, M constant, R constant, T constant. PV equals constant. Well, that's simply the shape of a hyperbola, isn't it? So we can visually see with our eyes the integral of PdV. We'll see that in a second from V1 to V2. It's a simple integral. Okay. Finally, it says, what was the heat transfer? We're going to use the first law to find Qn. Let's see. First law, closed system. Qn minus W out equals delta U. Well, what's delta capital U? That's M, the mass, times the integral of CV dt. Well, we don't even have to look up CV because what's dt for this process? It's isothermal. So the right-hand side of the first law becomes 0. Qn is going to equal work out. All right, let's keep going through the numbers. All right, let's do the first part first. Let's try to figure out the final pressure. We've got argon, so we'll look up. I didn't remember the molecular weight of argon. It's 40. So we'll put in the molecular weight's 40. We'll solve for the gas constant R for argon, R bar, 8.314 kilojoules per kilomole. Okay. We're going to enter our given numbers. M is 0.1 kilograms, initial pressure 200 kPa, T1 280 degrees K. So we're going to solve straight out for V1 using the ideal gas equation of state. V1 is 0.0291 cubic meters. Well, V2 is double V1. That's pretty easy. So we'll double V1, we'll get V2. Back to the ideal gas equation of state. P2 is MRT2 over V2. And so we've got P2 is 100 kPa. It's half of the initial pressure. All right, great. So we're a third of the way there on our homework problem. What's the work? Well, I hope you immediately know we're going to draw a pressure volume diagram. We're going to draw the process path. We'll look at it with our eyes. Well, that's a hyperbola. PV equals constant. That's a hyperbola. Okay. And then we're going to write it. We'll do the math, right? Work out as the integral of PdV. Well, let's see. P is MRT divided by V. That's the ideal gas equation of state. M is constant, R is constant, T is constant. We pull that out of the integral, so we've got the integral of dV divided by V. That's the natural log of V2 minus the natural log of V1. Well, that's just the natural log of V2 over V1, isn't it? Wow, so we've got an easy formula that we derived ourselves, not looked out of the book. Work out as MRT log, natural log of 2, since V2 over V1 is 2. Okay, so we'll do the numerics and we get the work out as 4.03 kilojoules, keeping our units straight. We're 2/3 of the way there. We will write the first law of thermodynamics for a closed system. Qn minus work out equals delta U. No change in kinetic or potential energy. On the right-hand side, we observe our process was isothermal. So dt goes to 0. Right-hand side is 0. Qn equals work out. And that was the nature of my question to Dr. O'Brien in the master's level thermo class. He got a grin on his face. Some of the students, there weren't any students rolling their eyes that Jay was asking this really moronic question, right? But they kind of kept quiet. And I said, doesn't that violate the Kelvin-Planck statement? We're transforming heat directly into work. And I just described a problem where we did that. And we do that over and over again. And he kind of smiled. And here was his answer. So Dr. O'Brien reminded me that the problem I described does not violate the Kelvin-Planck statement. He said, well, Jay, what you just described, that was a process. That was not a cycle. That what you just described was process 1 to 2. And so that's definitely possible, okay? Remember that a cycle, over here on the left, a cycle it goes through some special process, 1, 2, 3, 4, 5, 6 to 20, back to 1. That's what completes a cycle. You have to start and end at the same state. Okay. And so the little example problem I described in class was not a cycle. It was a process. And so, boy, Dr. O'Brien answered that question so respectfully. He didn't make me feel like a dum-dum. Okay. I kind of kicked myself for not asking Dr. Jones as an undergraduate the same question because I was so afraid that Dr. Jones would shake his hand and say, oh, I'm so disappointed in you, Jay, that you didn't pick up on the subtle point that what you just described was a process and it was not a cycle. Well, at least I got the courage to ask that at the graduate level. And so I want to encourage you folks to ask questions in class when you have some confusion as well. I don't think your instructor at this point in time they won't yell at you for being a dum-dum. I didn't feel like my question was that dumb at the time. I do see now, I'm so glad that Dr. O'Brien cleared that up for me, reminding me what I should have picked up, that what I described, that transforming heat into work, that it's possible because it is a process and not a cycle. So here's the recap. It's impossible to operate in a cycle and transform heat directly into work. That's the Kelvin-Planck statement. What is possible, it's kind of sort of my question in class, is it possible to transform heat into work? Sure it is, in a process, but you can't do it with a cycle. So that really helped clear things up for me, and it improved my understanding of the second law. Now, finally, a historical recap. What got my wheels turning in asking that question? Now, I showed a little cartoon of a dinosaur here because this cutaway and this image of a locomotive steam engine is a mechanical dinosaur. There are no more commercially operating steam engines except in the tourist and historical and entertainment areas. So yeah, commercially and for industry, the steam engine is now a dinosaur. But that's what had my wheels turning, and that's why I wanted to ask the question, because I was thinking about a steam locomotive where this engineer and fireman are adding heat in the boiler section, they're creating steam, and they're doing work in this piston to drive the locomotive wheels. And so in this image, you say, well, what's this stuff coming out here of the bottom of well, that's the exhaust steam. That's the spent motive steam coming out, exhausting from the piston, the driving piston that's driving these wheels. And so now that I look at it in a little more mature manner and with better understanding, I see that this steam locomotive is not operating in a thermodynamic cycle. You see, actually, it's an open system, isn't it? Because you've got steam being produced in this boiler section, and what's coming, and once that high pressure steam is utilized to drive the wheels, steam is exhausted into the surroundings. So that is definitely not a system operating in a cycle. Okay, I hope those remarks help you in your understanding of the second law, particularly the Kelvin-Planck statement. Remember that there were three statements of the second law in Chapter 5. Really, all three of those statements have to do with what's possible and what's impossible. And so that's sort of what pulls those three statements together. It can be confusing, can make you think pretty hard. I want to thank that student for asking the question about the Kelvin-Planck statement, because it caused me to reminisce back about my own undergraduate experience and some of the questions that I had myself about the second law. So there you go. Don't hesitate to go back and look at some of the previous videos about the second law in Chapter 5.